Hello, welcome again. So this is the last part of what I'm calling lecture 2, and basically this covers the rest and probably the most important part of chapter 6, which is section 6.4, where we look at implementations of some quantum circuits that does modular arithmetic. So this will get probably a little bit involved and more requires more time from you. Probably you need to read the book. Maybe you can go over some of these sections again, but it's going to be a little more algorithmic in things. So the operations or the algorithms we'll develop here are more general, though some of them are not the most efficient of these algorithms. But to get to the most efficient algorithms later, we need to see these more general ones, which are easier to understand, but they requires more complexity or more time, more circuits, more gates, etc. So when we get to Shor's algorithm, if we get to it, the arithmetic operations used there are more efficient, but the ones we are using are more general, so there is trade-offs. So in general, in most of the modulus arithmetic we will use, we will have the modulus we work with, which is big M, is going to be placed in a quantum register. So let us move on. So the first of these things we want to implement is an efficient implementation of AND. We want to get to kind of a linear implementation in AND in terms of complexity. Basically, we want to do a generic M-way AND or conjunction operation that's computed into an output qubit using only one additional temporary qubit. So, like in most of the implementations we'll get to, we kind of do things in a modular fashion or in a function fashion. So we'll generate some functions we know that we will use in the later things. So you'd see that this AND is going to be used in later things in this lecture. So this is kind of a little bit of a longer lecture, so you need to have some coffee, take your time, block time for it, and go about it. So we first implement what we are calling a flip function. And a flip function is basically kind of a generalization of a Toffoli gate, which we use the symbol T for it. So flip acts on an M qubit register, we're calling it A, and that A has bits that go from A0 all the way to AM-1. A0 is the lower order bit, AM-1 is the higher order bit, so this is M bits going from 0 to M-1, beginning to end. And we have an M-1 qubit register, we are calling it B. Note that A is M bits, B is M-1 bits. So B would go from bit B0 all the way to bit M-2. So that is an M-1 bits. Now, what flip does, it negates the qubit B sub I exactly when I plus 2 conjunctions of the bit A, of the register A, of this form. Basically, it's AJ conjunctions going from J0 to I plus 1. So J from 0 to I plus 1, basically this is I plus 2 bits, is true. So if this conjunction is true, then we negate bit BI. So this is a generalized form of a Toffoli gate, so multiple control bits. If the AND of all those is true, you inverse the target bit. So let us kind of decompose this a little bit. If we pick I to be m minus 2, then I plus 2, which is in this, would be m. And then I plus 1, which is be the bound here, would be m minus 1. So, thus, for an m-bit conjunction of bits A0 all the way to m minus 1, you can write it the other way. I'm writing it here, not meaning anything, but I'm just trying to reason about it so that you understand what's going on. So those are m bits. If we do the conjunction of those bits of A, that would be meaning if and only if the conjunction of these bits going from 0 to m minus 1, meaning m bits, equals 1, then b sub m minus 2, which is b sub I in this case, I'm taking these values and I'm trying to see on the registers A and B we have used what happens. So bit m minus 2 will get negated. If we go back to the bit m minus 2 is basically the most significant or the highest order bit in register B. That bit would be set to 1 if all these bits, when you do a conjunction of them or you do an AND of them, it turns out to be 1. Basically, when all of these are 1s, you'd set this bit, you'd negate this bit or basically set it to, yeah, you negate it. If you start with a 0, then it would be a 1. If it was already a 0, you would set it to a 1. If it was a 1, you set it to a 0. So this is the most significant bit of B, or the highest order bit in B. This would allow us to define flip in terms of Toffoli gates that would perform bit flips on some qubits of a register depending on the contents of register A. So now let us do a case where m equals 2. So we would define flip on a register, a quantum register A of 2 bits, and an output register B of a single bit. So A of 2 bits, so Toffoli of A1, A0 would negate B. We negate B if both A1 and A0 are 1. So the general case, this is the base case when m is 2. The general case would be when m is larger than or equal to 3. And basically what we would do here is we do flip on A of m bits and B of m minus 1 bits. Not that A and B is always 1 behind this. So in the case this was 2, B was 1. When this is m, B is m minus 1. So what do we do with this? First, we do this we want to do this on the m bits. So we are going to do it one step at a time, and it will do this kind of in a recursive way. So we do first Toffoli of A m minus 1 with B m minus 3. Why B m minus 3? Because that is the bit that's next to, if we go up to the bits in the register, B. Bm minus 2, Bm minus 3. So at the beginning, we are doing Toffoli between this bit and this bit, and we are storing the result in M2. Okay? We are doing Toffoli between AM minus 1, Bm minus 3. We are putting the result in Bm minus 2. Now, we do flip on 1 bit less of the rest of the bits. So when you look at A here, A goes from 0 to AM minus 2. So this means this is an M minus 1 register. So we took out M minus 1. We took out from here the bit that we stored at PM minus 2. And then we took this as well. Then we do flip on these bits. What happens here is you look at as these bits. If all are 1, you set this bit, right? When this happens and finishes, then you go back and you restore what you have done here to get the old value of Bm minus 2. And that's it. So basically, this would go and compute negate the bits in B for the bits in A in each location. So it does it recursively on each set of bits, and as you come back, you take the previous result, result that you got in B with the next bit in A, and then you store the value here, and you move on like that. So basically flip on an M qubit register A and an M-1 qubit register B. This would use, since the recursion steps in this are M-2, you would repeat this M-2 times. And since we are doing this, and we are doing this twice, here and here, so these are the two Toffoli gates, and then we do steps in this M-2 until we do all the bits. And then there is the final one bit, which is the base case. This would give us the number of Toffoli gates we would need to compute this. So it's 2 times M-2, the recursion steps, plus 1. So now we define an temp, which is an operation on 2 M-1 qubits that uses M-2 additional qubits computing an AND on M bits. So too much going on here, but we will decompose that later here. So we want to compute AND temp, which places the conjunction or the AND of the bits in register A and the single bit, the single qubit register B. And we make temporary use of the qubits in register C. So the base case of that AND temp is not that. The flip that we defined up, we will use it here. So we do, the base case is an AND, a quantum register A of 2 bits and a quantum register B of a single bit, basically a single qubit B. And then the AND temp of this is Toffoli of A1 and A0, and then you put the result in B. Right, so you start that bit B in 0. So basically, it's so you are getting AND A1 and A0 into B. Now, let us go to the general case. The general case when M is greater than or equal to 3. So we define this. It operates on A of M bits, B of a single bit, because the AND, the result is a single bit, and then we use C of, this should be a bracket like this here. That's a mistake, sorry. M-2. So this should be a bracket that's similar to this one. So we have AM, right? M bits. This is M-2 with the output result B. All of this would be basically M-1, similar to the flip. So let us apply flip at the beginning. So flip between A and the combined register of C, which is M-2 bits, plus that B, which is another bit. So this would be M-1 bits and M. So then what this means is this would put in B, would negate B basically once if all of A is, the bits in A is a 1. Now let us in that combined register, what we can do is do flip of AM-2. Note that this negates B if all of A bits, the bits in A are 1. So basically, if B is starting with a 0, you would put a 1 in B if all of the bits in A are 1. Then if some of the bits in A are 0, then the conjunction of them or the AND of them would be 0, so B would remain 0. So basically, B now would hold the outcome of the AND operation of all the bits in A. Now we want to uncompute C. So to uncompute C, what we do is we take the rest of the bits of AM minus 2 all the way to 0, and then in C, this would do the uncompute of C. We cannot do the repeated with B because that will remove the result we have in B, but we need only to unentangle C. So that's why we do the same flip operation between AM minus 2 all the way to A with C. So now let us look at the complexity of this. So that's why the flip here was kind of the needed underlying operation for the AND operation to happen. So in step 1, this is the regular flip we have, so it would be 2m minus 1 plus 1 t gates. In step 2, it would be m minus 3 times 2 plus 1 t gates. So overall, this would be 4m minus 2 gates. If we do the math, this would be the 4m minus 8 if you add these together. So after AND temp, basically we leave register C as it was before AND temp. This does an uncompute in C, so you restore C to its original value. So regardless of the beginning value of C, we return it back to what it was before. So we can now use that AND temp to build an AND gate on n qubits using only one additional temp qubit. We use we recursively use AND temp, and basically what we do is we use AND temp on one half of the qubits and use the other half of the qubits as temporary bits, and then do the reverse to get all of the AND on all of the operations. So basically, if we have m bits, we let k equal m over 2, and then we do the floor of that. And then we define j to be equal to k minus 2 if m is even, and j would equal k minus 1 if m is odd. And now we use these values, j, k, and m, in our computation of an AND. And basically, AND flips B if all bits of A are 1. So we define this, the unary case, the case where m is 1, basically when A0 is 0, we do C naught on A0 and B. And basically this would flip B if A1 is true. Basically, we could write this as B0, but it's a single qubit anyway, so it doesn't matter. Now, let us do the case when it's binary. So basically, define AND for A of 2 and B of 1. Then this would be a Toffoli gate. So that's what we expect. So nothing here unordinary or that we haven't seen before. Now we go and define AND for the general case where m is larger than or equal to 3. So A of m and B. Now we define a single qubit, T of 1. That would be a temporary bit that we need to use. And then we'll use half of A to do AND temp on. So we reuse AND temp that we have used between A of m, right? So A of m, A goes from 0 to m minus 1. So we split it by k, as we've done up here. K is half of it, m over 2. So we go from am minus 1 all the way to ak. We do the higher order bits first. Then we do AND temp of this with t. So t will hold the result of this, and then we use these bits to be the C bits in AND temp. We use it from AJ to A0, the lower order bits. And how do we get J? We get J from these equations. It's either K minus 1 or K minus 2, depending on if M is odd or even. And if you you should go convince yourself, pick two values of m, let's say 8 and 7, do the math to come up with these numbers, and then do the math to come up with what values these would span, and it would be, lo and behold, the values you want. So T here would hold the AND result of these bits, AM minus 1 all the way to K. Now, let us go and do the computation on these bits. So now we take these bits over here, then we take the bit B, the final output B. So this is gonna do an AND of all these bits. T holds the AND of all these bits, and then these bits would be the same after the AND temp, because we said AND temp does not change the C bits here. So these are similar to the C bits in that AND temp that we defined before. So once you come out of it, you still have your values there, you do not change them. And then now we do B, which will hold the final result, and then we use these bits, the higher order bits, to define this. So, and here it's AK plus J minus 2, and this is gonna be the right number of bits from AK to what you need. Then after that, what we need to do is we need to undo the operation on T to restore T back, to uncompute the value in T. So step 1 in this is basically computes the AND on the higher order bits, like what we have said, and we use as temporaries the low order bits temporarily. Then step 2 does the computation, the AND on the lower order bits, right? And it uses T to hold this with it, and you need to convince yourself of how many bits are those, plus 1, and then you get this, and then this would be smaller in total number than this by 1 bit. So we compute and then the step 3, the result would be in step 2 in bit B. This is the AND of all the bits, the lower order half and the higher order half. And then step 3 uncomputes step 1 for T, basically. And note that AND temp keeps register C in AND, which is this and this both unchanged. So A does not get changed because of this operation. Thus, only we need to uncompute T in step 3. So there is a lot here. It builds on a lot. You need to go back up and go back again and map these bits to what AND temp uses. This is what you are computing the AND on. This is where the result is, and these are the temporary bits. And the golden thing about AND temp is that it does not change this. It uncomputes it. Once it modifies it, it uncomputes it before it exits. So in this and this, you do not change neither this portion nor this portion of register A. So register A comes out of this unchanged. Okay? So let us move on to the next thing, which is an efficient implementation of a multiply controlled single qubit transformation. This is section 6.4.2. So an efficient AND, like what we have implemented thus far, would allow us to do a linear implementation of what we have introduced in the very first lecture we did before, which is section 5.4.3, which is a conjunction on X sub I of Q. So basically, we want to do, given m bits string in Z, we define X of Z to be this particular transformation. Basically, Z has a 0 bit. We would have a 1. So when there is an X, Z has a 0 bit. When there is an I, Z has a 1 bit. And then we define a conditional on Z and Q, and basically it acts on qubit B with Q if and only if the bits in register A match the bit string Z. So let us see how do we implement this and detangle what it has. The pun is intended. So let us define a conditional on Z and Q that operates on the quantum register of M Q bits A and bit B. We use a temporary Q bit of T, and then we do this operation. We negate, we do X sub Z on A. So basically, if A and Z match, A is all ones. If these match, A is all ones. Now, let us do an AND on the bits on A and then set T with it. So basically, this does the matching between A and Z. If the matching happens, all of A is set to 1. Now we do an AND on A. If this match happened, then all of A is 1s, and then we would set T to 1, right? Now, let us take T. If this match didn't happen, then this AND would produce a 0 here, right? But if it produced a 1, then if the match happened, then T would be 1, and then we take 1 here and do a control operation on T, applying Q on B. So if T is 1, i.e. A matches Z, then apply Q to B, right? Then we are applying Q to B in this case. Then we do an uncompute on this. This is what we need to do at the end. This is the result that we need to do. So we uncompute T, then we uncompute the match. And voila, we have done we have done this. Now, it's your job to analyze this and determine how many temporary bits did we use in this algorithm. You need to go back and check how many temporary bits and uses, how many temporary bit this uses, and answer this question. Now, let us do an n-place addition. So now let us do n-place addition. So n-place here means you are adding 2 values and putting the result in one of those values. You are overwriting these values, not adding 2 values and producing a 3rd value. That's why it's called n-place addition. So here we will add basically 2 n-bit binary numbers, and the transformation would be something like this: C, A, B, and then we produce C, A, and then B here would be overwritten in the output to be A plus B plus C mod 2n plus 1. So 2 to the n plus 1, this is the n bits, so we go 1 extra bit with this. So A and C are n qubit registers, B is an n plus 1 qubit register, and since B is gonna be what will hold the result, we need n plus 1, right? Because it might get a carry, an extra bit, and we need to limit it to it. And also we would use it as a temporary bit. So we add 2 n-bit numbers placed in registers A and B and put the result in register B, hence the naming of n-place. So register C and bit Bn are initially 0. This is a crucial node to understanding this algorithm. C is initialized to 0, bit B sub n, which is bit number n plus 1 and register B, are both set to 0 initially. We will use n recursion steps in this algorithm, and we will use the sum and carry equations from section 6.3.2 and lecture 2 part 2 in the notes or the video that I uploaded before this video. Okay, so let us look at this, at the base case where n is 1. So basically, 2 single bits we are trying to add. So C, which is the temporary, A, which has 1 bit, and then B, which has 2 bits, B1 and B0 and B1. B0 is getting added to A, and then the result is put in B. So the first step in this is to use the equations that we have developed in the last lecture video and notes for carry and sum. So we would do C, A, B0, and then B1 would hold the carry, C, A, and B0, and thus the sum would be stored in B0. So B, bits B0 and B1 would hold the sum and the carry. Now, the general case where n is larger than 1, we define add to be C of n. This is set to 0 initially, A of n, and then B of n plus 1, and we set in this bit Bn to be 0. Now, let us see the steps in this. So, a carry of C sub 0, A sub 0, sorry, compute the carry of the 0 bits, and then we store that in C1. Not that, we need C1 or the bits in register C to be 0. So basically what we are doing in this is initially C1 is 0, so we are overriding it here. Initially C0 is 0, so we are adding A0, B0, right, with 0 in C0 and storing it in C1. So C1 is doing temporary result holding for us. Then we do the recursion step. We take this and apply it, but with n minus 1, n minus 1, n. Not that, we have used B0 and A0, so we shrink the bits and move to bit position 1. We've done the initial addition of A0 and B0. We move to A1, B1, and we use C1, right? So C1 has been computed here for the carry that's coming out of those. If this bit is 1 and this bit is 1, right? The sum would be 0 and the carry would be 1. So we need that carry in the additions of the next bits. If you have done digital logic, you know this. This is being called Rieffel counter, right? Your Rieffel adder. You add the bit 0 together. You have a sum and a carry. You take the carry to the next sum, and then you do the addition there, and then you move on. So what we need for the next addition is the carry. The sum will be produced later, right? Okay. So we take that bit C1, we do the addition for bits n minus 1 going from C1 all the way to Cn minus 1. So these are n minus 1 bits because this is starting to count from 1. And then we use with it bits in register A going from 1 to n minus 1. So this is n minus 1 bits. Then we do B1 all the way to Bn, so these are n bits. So this is exactly calling this function, but instead of calling it with n, we are calling it with n minus 1, and we are shifting the register 1 bit to the left. No, we are not shifting, but instead of using all the n bits, we are using n minus 1 bits going from bit 1 to bit n minus 1. That word shifting is wrong. We'll use shifting later when we get to multiplication. So basically we are just going to the next bit, and then next bit, and then next bit, and then next bit, until we do all of the additions there. When we come back from that recursion, we need to undo that carry above, so that we leave C unharmed, untouched. We uncompute the value in C, and then we do the sum between bit C0, A0, and B0 and store the value in bit B0. And that's it. Because of all of this is because of the recursion that we are doing in this. Now, we have done in-place addition. Let us go do modular addition that's not in place. And if you think about it, we're gonna need that in-place add that we have developed now. The key here is we produce the result. We add A and B together, put the result in B, and we leave C uncomputed. Basically, we leave C as it was, 0. So modular addition of n binary bits, A and B, or n binary registers, or n binary numbers, A and B, we do add mod A and B, and then the modulus, which is n, is in one of the registers, one of the quantum registers. Then we'd get out A, and we would get in B, A plus B mod M, and then M out. So registers A and M are n qubits. Register B is n plus 1 qubit register. B sub n is still initially set to 0, similar to what we have done above. Register B stores the result, i.e. its contents are gonna be modified to hold A plus B mod M. Register A and M and any temporaries are unchanged after add mod, which is the modular addition. So register A and M and any temporaries are unchanged after add mod. So we have to do all our uncomputations to A and M to leave them unmodified. A and M will be unmodified after this. Okay, now let us look at the algorithm. So if you wanna go pause this, go have some caffeine and come back, that would be fine. So define add mod on A of n, B of n plus 1, and M of n. We are adding A and B, each has n bits, into register B mod M. So qubit T, temporary bit. Qubit T is a temporary bit we will need. We need C of n qubit, that's for carry storage, and initially, whatever it is, we don't care, we're gonna restore it later. Now, we use add from before of C, A, and B. Add A to B and put the result in B. Okay? Now B is n plus 1 bits, A is n, and C is n bits. If you remember, if we go back to this, we restore, we set C to 0, but we restore it back. Okay, so in add C, A, and B, we do the addition, get A plus B, put the result in B. Now, since we are doing modulus to this, we need to check to see if the result in B has gone above M or not. So we need to do add minus 1, which is basically a subtract. Add minus 1, C, M, and B. Basically subtract M from B, put the result back in B. So if this happens and there was an underflow, basically when B minus M, so subtract M from B, basically we are doing B minus M. If B minus M becomes negative, we will see bit Bn to be a 1. Basically, this is a sign of underflow. So then what we do is we toggle bit T when B sub n is set. And B sub n would be set only when an underflow happens. So if this happens, we would negate T, and then we would do a control operation on T. If this happens, if an underflow happens, we come back and add M to B to restore the value back, M plus B back. We should not have subtracted. The value is still within the bounds of M. So then we do add -1 here to restore the value of C. Basically, we do this to uncompute C back, restore C back to its previous value. Then we do uncompute on T. So we do inverse of B and control X of T, uncompute T, and then at the end, we need to go back and get the final result. A, B. Not that. C goes unmodified from add. But since we have done this here, to roll back what the value of C, since we have done the modulus here. So this is all what need to happen in a regular computation, and this is for the reversibility of the operation. So in step 4, if M is larger than B, then B minus M would be negative, and then Bn will be set to 1. Steps 7, 8, and 9 would reset the computation on T, or uncompute T. Also note that internally, every add uncomputes C back. And for add mod to work, we need to have A to be positive, greater than or equal to 0, and we need to have M larger than B. If these conditions do not hold outside the range of these values, then the operations become non-reversible, i.e. non-unitary. So if B is larger than or equal to M, unlike this, basically what needs to happen here, if you think about it, if it's larger than M and you subtract only M once, and you are adding P plus A, there is a chance that this grows more than 1 time more than M. So, and we subtract only, do the modulus, we subtract M only once, right? If it grows more than M twice, for example, more than twice M, then we need to subtract multiple times. And this is not what the function is being programmed, or the algorithm is designed to do. So these are the bounds of this. Now let us move to multiplication. So since we have done addition, we can do multiplication. So now we do modular multiplication. So we call it times mod. Basically, it multiplies two n-bit binary numbers, A and B, modulus another n-bit binary number, M. So times mod A and B and M, all these come out back without any change. And then the result is gonna be stored in B, and it's gonna be B, the initial value of B. You need to set that to 0 right at the beginning, and then you add to it B times A, and then all of this modulus M. So this program would successfully add B sub I to the power 2 of I, A, mod M to the result in register B. Note that B sub I, this is the bit value. 2 sub I, this is the bit weight of this. If you have a 1 in any bit position, the value of that one comes from that bit position, right? If this is b sub 0, then the I is 0, then this is 2 to the 0. If this is b sub 2, then this is 2 to the 2. So you go 2 to the 0, 2 to the 1, 2 to the 2. So the bit position matters. The bit position gives you the weight of that bit. So in doing a multiplication, this is how we do it. Now, one other thing, A is less than M, but B can be an arbitrary value. And then again, bounding this so that we do not overflow. So A and B are n+1 qubit registers. And the higher order bits are needed for intermediate results. Then we would need some shifting to get the power here. So that shifting is, if you have done any digital logic, when you do shifting of bits, if you move the bits, you shift them to the left. If you had a 1 in bit position 0, that one would be of a weight of 1. But if you move it to bit position 1, then the weight of that bit position has become 2, right? So shifting left multiplies by 2. Shifting right divides by 2. So we do here what's called a cyclic shift. And basically we swap bit AI plus 1 with AI for all i's starting at a higher order, at the higher order bits. We swap bit AI with bit AI plus 1. So we moved bit AI to a higher order bit. So we have given it a higher order thing, a higher order weight. So AI moves to AI plus 1. Thus, we are multiplying by 2. That is going to be needed in the algorithm. So define times mod bit. The first register is an n+1 qubits in A, B of K, and K, by the way, this can be arbitrary, as the algorithm says here. B is arbitrary. B can be anything. We have no limits on B of K, but A has to be less than M. So B sub K, so this is K qubits, M of N, and then the result is P of N plus 1. Now, let us define first T of K temporary bits. That is for basically this matches with this, right? And then we need, for additions, we need the carry register temporary. Now, this is the first time we see in algorithms here a for loop. That's an iterative algorithm. So this goes for I that in the range of 0 to K minus 1. So this iterates through the B register bits. These are what we are multiplying, right? A times B. So A is what we are multiplying B by. So we are going through what we are multiplying in B bit by bit. That's why we are iterating over K. So this is our K things from 0 to K minus 1 for each of the bits. So at the beginning, let us subtract A minus M. Doing A minus 1, use C, M, and A. We are doing this to know that, to see if A is bounded by, is less than M or not. So once we do this, we check bit A sub N. This is similar to the modulus we have done before. And then we do this A sub N control negating the TI bit. Negate TI bit. So basically set TI to 1 if and only if M is larger than A. So if this goes an underflow, if A is less than M, then AN will be set to 1. Then we come here. If an is set to 1, then we set ti to 1. Now, note that when we do temporary bits like this, they are set to 0 at the beginning. So ti, which is set to 1 because of this, we do control on addition on that bit ti. So when ti is set, we do the addition. Basically, we do that addition back. We do a plus m if ti is set to 1, i.e. m is larger than a. Note that we are doing this for the modulus, so that's why we need to do that check. Now, we take bit bi and do a control operation on add mod of the bits an minus 1 from 0 to n minus 1. So these are m bits with b and m. Recall, this is the exact thing we developed in the previous section. So basically, we would add a to p if pi is set. Otherwise, i.e. if pi is 0, we do nothing. In binary multiplication, we skip 0 bits, basically. So we are gonna add this to the result. We are gonna add a to the result if bit b sub I is 1. If bit b sub I is 0, we don't need to add a because we are multiplying a, all the bits in a, by a 0. If we are multiplying it by a 1, we need to add it to the multiplication result. Now, since this is a multiplication, we need to do a shift on a. Right? Remember, we do a shift on a, multiplying it, shifting it to the left, thus multiplying it by 2. So this is similar to what we do in binary multiplication, right? When we are doing the multiplication, we do the first bit, we write the result. When we move to the next bit, if it's a 1, we copy a, but we shift it by 1 bit position and then do the addition. That's exactly what we are doing here. Now, this is basically what this loop needs to do. The loop would go iterate on each bit, checks if we are within the modulus range for A or not. If we are, then we do, we go and move and add that register A into the sum bit if BI is 1, and then we mod that by M, and we keep doing that for all of the bits like what we do the multiplication we are used to it. Now, in a classical computation, we are done by this. But since we are in a quantum computation, we need to do uncomputes to T and A. So we need to take that loop, replicate it, undo things to restore the values back. Basically, we need to restore the values for the T register and the A register since we shifted it. So we do again for loop on I, but we go from k minus 1 to 0. We go the reverse of what we did. We do things reverse. So shift A, we shift minus 1A. Basically, we shift minus 1, and instead of shifting this way, we would shift the other way. Now we do T sub I control add minus 1 C, M, and A, and if you go back here, you'd see the TI control add this, so we do add minus 1 on TI. So then we are trying to restore back C. Then we do A sub N control X TI, this would uncompute bit TI, and then we restore the last thing for C to restore it back. And we are done with multiplication. Now, the last and most complicated among all those, if the previous was not complicated enough, we are doing exponentiation. Once again, You need some coffee and some caffeine. Stop this and go back there. This is an exciting thing because we do some things that John has told us in his lectures that we cannot do. We are going to be able to copy values in registers. So if this is not exciting enough for you, I don't know what would be. So modular exponentiation, basically exponent mod, exp mod would take bit A, bit B, and then M, and then bit 0, and would produce A, B, M like they are, and then in place of 0, it would produce A to the power B mod M. So this would use order n square temporary qubits. A, B, and M would be n qubit registers. M is the modulus, A and B is the values we want to use. So we need to define two auxiliary transformations. An n-bit copy, yes, we can copy values, but we cannot erase values. We can restore values, not erase them. We can copy as well. So our XOR operation is gonna show that it's really useful in a copy. So an n-bit modular squaring function is the other thing that we will do here. Let us go to a copy. Copy, not a move. We copy A into B without modifying A, but just copy B to A. Note that B has to be 0 to begin with in order for us to be able to copy. This would produce A, and the XOR of A and B, if B is 0, A XOR 0 would produce A. So we have copied A into register B, copied the contents. B has to be initialized to 0, or that XOR would not work. So how do we do copy? So define copy A of n, B of n. We do a loop and do A sub I control X B sub I. Basically, we are doing a bitwise XOR between the bits in BI in A and B. A sub I, B sub I. If B is instantiated to be 0, then A sub I XOR with 0 would be A sub I. So we've copied into BI A sub I. Now, square. We'll need the square in doing exponentiation. We'll see how in a little bit. But square mod, take A, M, and then S as the result, and you produce A, M, and then the result would be S, which is the initial value. That would be 0 plus A square mod M. So define square mod. We can do it. A for bit A is a register of n plus 1 bits. M is an n bit thing. S is an n plus 1 sum. Note that A sub n and S sub n here are gonna be extra, but they are needed for other purposes, as we will see in a little bit. Similar to what we have done in the add. We would need an n temporary bits and register T sub n or T of n. Then we copy these are n bits, right? So we are copying bits A0 to AN minus 1 into register T. Note that we left A sub n. Now we do times mod A, T, M, and S. If we go back to the times mod that we have done here, A n plus 1, B of k, M of n, P of n plus 1. This times this, modulus this, into this. So let us go back into the squaring. So why do we need the copy? Because we need to multiply A by itself, A square. So we need to copy A into T, the bits in A into T. Then we take A multiplied by T, we mod it by M, and then store the result in S. This is what we have done here. So this is using the times function to produce the square function. Then, lo and behold, we need to uncompute T. So we do copy -1 of this to restore the value of T. Basically, we clear the T bits. Note that T starts with a 0 for that copy to work. Now, again, take a deep breath. This is the exponentiation. So, exponent mod A, B, M, and then B and E for the results. A, we would produce A, B, M, and then P, and then the result would be E XOR P, A to the power P mod M. So we define A to be an n+1 register, B is a single bit. This is basically the base case where we are multiplying, we are doing an exponentiation with a single bit register. This can go to any k bits, then m of n, then p of n+1, then e of n+1. Basically, we take that bit, b of 1. If that bit is 0, our result would be basically, we are doing a to the power of 0, so which is 1. So the result would be b if b of 0 equals 0, right? If b0 is 0, we are doing a to the power of b, and b bit b0 in b, which is a single bit, is 0, then a to the 0 is 1, then 1 multiplied by p, and the result would be p mod m. And then to do that, if bit b0 is 1, we do control times mod a, b, m, and e. Again, we are using the times mod from above. This is if b0 is 1. Basically, what we would be doing here is it would be e plus p, a to the 1 mod m. Now, the generic case where k is larger than 1. Again, it would use something similar to those, but with more things because we have a generic b of k. So, we need an n+1. So the generic case is a of n+1, b of k, m of n, e of n+1. So we need two temporary registers, one u n+1, v of n+1. This is u is gonna hold a square mod m, and then v will hold p times a to b0 mod m, if b, and then let us see the rest. Now, if bit b0 is 0, what we do is we copy p into v. So v would equal p a to the 0. b0 is 0. a to the 0 is 1. Then v would equal to p mod m. Now, if b0 is 1, then we do times mod a, p, m, and e. So if b0 is 1, then e would have p a to the 1 mod m. Now, we do square mod of a, m, and u. So we are squaring a into u mod m. A square mod M into U. This is the result of this. Now, what we have done above is we have done the computation, the exponentiation with bit B0. Now we need to move over to the rest of the bits. We need to look at bits from B1 to BK minus 1. So what we are doing here is we're doing a division by 2, because we are, instead of looking at all the bits, we're looking at this and we're starting from here. So this is similar to a division by 2. We take U from the square, then this, right, which is B over 2, because we've shifted this, shifted by 1 bit to the right. So, but we have A square, B to the B over 2, and then this together is basically A to the power P multiplied by V mod M, and then store the result in E. This would happen recursively until we do it for everything by shifting to the right. Now we need to do uncompute. So we need to uncompute U by doing square mod minus 1, A, M, and U, uncompute U. Then we need to do the same, the inverse of what we have done here, which is B control times mod minus 1, A, P, M, and E. This uncomputes E, and then the final thing is uncompute V. So this program unfolds recursively K times for the bits in B, once per bit of B. So this algorithm would require 2 K minus 1, 2 qubits, 2 N plus 1 qubits, N minus 1, N, blah, 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 2 N plus 1 registers, right? 2 N plus 1 quantum registers, U and V in this case. So each is N plus 1 bits, and we use 2 of those, and then we do the the recursion K for K minus 1 times. This is how many temporary bits we need. Times mod requires order N square steps, right? Exponent mod would require order K N square steps. We repeated K times in the recursion, and we need times mod each time of those, then the complexity is Kn square. This is not the most efficient exponentiation thing. There is better algorithms. One of those is called the Schnohag-Strassen. I'm probably butchering this guy's name, but Strassen algorithm. The book towards the end has a citation for it. You can go look at it. And if we do that algorithm is of order Kn log n log n. Definitely, this thing is much less than n. Let us see an example for this. Assume that n, the number of bits is 100, just for kicks, right? Log 100 base 10 is 2. Log 100 is 0.3. When you multiply n times log n times log n, you'd get 102.3, you'd get 60. N square is 10 to the 4. So instead of having here, this is kind of 3 orders of magnitude reduction. So this algorithm is much more efficient than the other one. Okay, so we've covered a lot in this. You need to take time, think about this, stop it when you need to, go over the things again, go read it from the book, and enjoy. I think if there is anything that you wanna enjoy the most about this is the fact that now we can copy values, so we can do computations. So in quantum computing, we can copy values. Okay, thank you guys, and I hope that this is helpful. and I hope that the recording will be good. If you can, if you have questions, again, I'm gonna open the discussion for the questions, but you needed to go over everything together to do this. Take your time with this, and good luck with your projects. And now my portion of the quantum computing class is done. Jay is gonna move over for the next class, and good luck for him, because so quantum gets exponentially more complicated as we go, as you can see. So his stuff would be more involved. But I would advise you to go watch the Berkeley videos that I have in Module 0 with Professor Somesh from Berkeley. They are really helpful. Okay, good luck, guys. Bye-bye. Submit your abstract for the projects.